Okay, let's start the Autodesk robot demonstration for this 5-part 2D chassis. You have done this by hand, so you got all this information already, including the dimension, cross-section area, and Young's modulus. And I also upload Excel file for you guys already, and then for you to validate your calculation. And then in that Excel file, there is VBA, or we call micro program. It's based on the Visual Basic uh, at the back of the Excel file. So if you really want to have a look how this program was coded, then you can also do so. So before you can then before you open that Excel file, open a blank Excel file from your computer, and then after that click on File, and then go to Option, and then after that click on Customize ribbon, and then you can select the Develop tab, which is showing in here. So if you click on Developer tab and then click on OK, then you can see the Developer tab is added to this menu screen in here. So after that, you can open the file I already upload to the Moodle, and then if you click on this one, will bring up this file in here. And then make sure that in this yellow band, make sure don't close this one. Okay, don't close this one, and then make sure you enable the contents so that this VB program behind this Excel table, you can see it properly. So if after that you click on yes, then you can see this file in there. So in this file, we have many data spreadsheet in here. So the main spreadsheet with numbers of buttons allow you to run this finite element analysis step by step. And then you also have the node information, including the coordinates of the nodes in here. And also we have the element information, including the starting node and end node, and what type of material, what type of cross-section is going to be there. So all this type is come from these two tables. So they give you the Young's modulus and the cross-section areas, and then also this boundary condition setting which node has the X or maybe Y that restrains, so that it cannot move along a certain direction. And here tells you which node has loading on. So I think if you read this data, compare with the join, you should be able to understand this easily. So after all this information, we should be able to calculate the element stiffness matrix, and then a global stiffness matrix as well. And then after that, if you assemble the global stiffness matrix, then you can apply the boundary condition as what we're showing in here. Apply the boundary condition and apply the loads, and then you can partition the matrix. So the partitioned matrix is going to store in this file. You can see that we'll separate into 4 blocks. And after that, we need to resolve this simultaneous equation. In our case, the one we need to solve is 4 by 4, and then we use the Gaussian elimination to do that. So regarding the Gaussian elimination, that's including in the first class I upload reading materials about this mass review. You need to have a look at that details as well. So after you resolve this matrix, you should be able to have a look at the displacement in this tab, and also the reaction force in this tab. And after that, you should have the member force. So for each member, either the under tension or compression, they should have this member force in here. Then after that, because tension and compression, they have different design procedure, we separate these two. And then for the tension member, then they will automatically select the proper dimensions. Now at this moment, in this program, we only use the circular hollow section. So this dimensions is picked up from this table, the last table in there. And then after that, we'll select the proper tension member for this 5-bar chassis. And then the compression members, I haven't completed the program yet. and then if you're interested in, you can continue to do the compression members as well. This is purely from the section property table. I just copy and upload this file in there, and then I guess if you done the year 4, you should know all this information already. What is the tensile ultimate strength, and then for different type of the materials you are using in here. So as you can see, all this information apart from the last two, and then the other one between the first several and the last two, they all empty because we haven't run this program yet. So if you want to run this program using this our maybe homemade that finite element program, then you can have a look at by click on the read information. So first, read information basically just read in this for that cross section in here. So which including the nodes of the building, the charts, and then also the elements and materials, cross sections, boundary, and loads, and all read into the memory of the computer. So we store in somewhere in the array we define in the VBA. So if you really want to see how this after I click on read information, what has been done behind the scene, then you can click on the developer bar. Then you can after that you can click on Visual Basic, and then so they will bring up this background information for you. Okay, so the first one is the read data will call these subroutines in here. So these subroutines actually basically will clear out all these every cell. They clear out before we do the calculation, clear out all this data spreadsheet. So maybe they clean them first. So after that, we're going to read the basic details. For example, the read basic detail, and then this one. This line will call the next subroutine. So that next subroutine will be run after you finish clear out the tables. So on and so forth. All this program is in here. So if you're interested to read on this one, you can maybe set a breakpoint and then debug the program in here, like what I'm doing here by clicking here, and then you can come back to the Excel and Excel file in here, and then you can click on one, and then you can run the debug information. For example, after that, if I want to see how the program calculates the element stiffness, then what I can do is I can come back to this program here. So that's actually will call the first program in here. Let me show you. So I call the element stiffness matrix in here, right? So then what I can do is I can set a breakpoint in here. So I set a breakpoint in here. Then I remove the breakpoint by clicking on this one again, so I don't need to stop in here. So we already run the first one. So the first click has done. So which means the till here, read the cross section informations. That subroutine has been done already. So the program has run to here so far. Okay, so this is we finished already. The next one, we click on element stiffness. So let's have a look at how the element stiffness is working. So for element stiffness matrix, as you can see, the moment is empty. It's nothing there. So what we can do is that we can come back to here, and then if I click on the calculate the element stiffness matrix, and then you can see that will stop in here. So the first line is stop in here is going to maybe select, just make the element stiffness matrix. This worksheet will be the current activate one, right, at this moment. So what we can do is that if I run this program, one more line, so I cannot run this bit here. I need to, because if I click on run, he will finish and he will not come back here. So what I need to do, I need to use a debug. So debug, you can see the different program, they have different debug command. So in here you can either click on this line, and then the program will run line by line, or maybe you can press F8. So because I want to show you how I do this one, so every time I will press this one to let you see that what I'm doing. So I click on this line. So you can see this program will run one more time, one more line, and then when you come back to the Excel file in here, you can see now this worksheet of element stiffness matrix, this one is now activated already. So you can continue to run the program in here. So for this line in here, we're going to set the colors, format, and so on and so forth. So if I run one more line, so debug F8, and then that will show you that what I need to do here will maybe fill the cell with a certain color, which is in here. So let me show you. So if I finish this line, I do one more line, and then do one more line, and then do one more line, and do one more line, and then do one more line, and then so the end of this. So I don't have time to maybe explain what this line is doing, but if you're interested in, you can Google the Excel VBA programming. So they give you all this syntax, their information. You need to learn this one after class. So then you can do one more line. Now, so once this done, you can come back to the in this program in here. You can see this basically just fill one cell with this type of color in there, right? So this is how this program is doing at this background. So of course there's many information. This, I guess you possibly see this one is already E over L or all this information in here. So this actually is doing the calculation, the actual calculation in here. So once this done, then every cell was filled, and then you got all the data in there. So because I need to save some time to do the Autodesk robot, so I will stop here because we're not using the Excel VBA anymore, and then I just give you this as a tool, and then you can maybe to validate your hand calculation. So we're not going to talk about this in detail. Some students already use Excel VBA before, then they will be very familiar with all this one already. So once I done this one, so I don't want to do line by line, so I just simply click on continue, but without any breakpoint. This program, this subroutine will complete until this line, until this complete in here. So let me click on this one to see what's going to happen if I let it run continuously from that line on. So I click on continue or press F5 if you want. So if I come back to this program there, you can see all the element stiffness matrix has been calculated, and every location index or location that information also calculate and mark in here. Okay, so it's very convenient to do by this way. So because of this, I won't come back to that Excel VBA again. So I just show you how I can do this one. So I already done calculate the element stiffness matrix. Then I'm going to assemble the global stiffness matrix in here. So if I click on here, you can see now the program just put all these global stiffness matrix together to form this 8x8 matrix in there. Okay, then I come back to this one. I continue to set the boundary condition. So when you set the boundary condition, you can see then these 4 points are not movable, it's fixed. So you get the displacement as 0 in there. Okay, and then after that, what we need to do, we come back to this page, and then we need to continue, just follow this these procedures in here. So the next one, we're going to apply the load. So we click on apply the load. We can see this loading -10 and 10 has been applied to these two boundary conditions already. And then after that, we then will partition the matrix, and then that will store in this one in here. You can see this is empty at the moment. So this is a block without partition. So the next one will partition them together. So let's come back here and then to set the partition to matrix. Now you can see this one partition in 4 blocks. This is one block, this is another block, so on and so forth. So we already talked about this. Maybe we'll talk about this one after the partition. Then you need to solve this 4 block in here. Sorry, this 4 block in here. Okay. So sorry, this 4 block in here, because that's a V3 and U3, V3 and U4, V4 in here. So we need to resolve this one using the Gaussian elimination to find out the answer. So we come back here, then we can then click on the equation solver, and then that give you this triangular that global stiffness matrix, and then that's a force vector on the right hand side. So this is a displacement corresponding to U3, V3, U4, V4. Okay, so that's how we calculate this one out already. Remember, this data we're going to use the Autodesk robot to prove these results as well. So this is not finished yet, so let's maybe go into here and calculate this displacement. So the displacement now is showing in there. So, and for x direction, y direction, and then that's for node 1, node 2, node 3, node 4. Okay, so this is the information we're going to maybe come back after we use the Autodesk robot to check all the detail. They should be very, very close, maybe just a round of error difference between them. Okay, so once we got this main this what I call the displacement down, then we haven't calculated the member force yet, so we can use calculate the member force to show you and what the member force for each one. So that's showing in there already. So 5 bar we got in total, and one is a 0 force bar, but all the other one has either compression and tension in there. So that's all the final element we going to have. So because oh sorry, not finished yet. This is to the member force. There's one last things we need to do is for the reaction. So we need to calculate the reaction. So we need to calculate the reaction. Then that give you this force in node 1 x direction, how much the reaction force it is, and then node 2, node 1 x direction, node 1 y direction, and then node 2 x direction, and node 2 y directions as well. So that's actually basically our final element will stop here. So the continuous one will be the design. So if you got a member force, you want to do the calculation to make sure that the capacity are adequate or not, then that belongs to the design procedures. So in final element is so much easier. If you get all the member force, you can continue use the program to do this automatic design. In our program, in this subroutine here, select the tension member. The program will automatically select the appropriate circular hollow section size for that member force for that length is given. So if you're interested to do further, you can have a look at this program yourself after the class. And then what we're going to do is that I'll maybe stop here, and then you need to move on to the next slide. We start to talk about the Autodesk robot to how we can use the commercial software to analyze this type of structures, and then we'll also give you the same results as well. Okay, now the second part of our demonstration is the Autodesk robot. And then to access to the Autodesk robot, if you log into any university computer, and then you can go to your main screen. I think you saw this one. Possibly your student version is slightly different from what I got, then but it's very similar. And what you got is that very important bit is the apps anywhere. So if you click on apps anywhere, that will take you to this screen. So when you click on this one, you may ask to key in your password, username, or this one using the Napier the login detail to log into this part. Then after that, what you can do is that you can then key in the robot in here. So you should be able to see the Autodesk robot computer in here. Because my computer I'm using this one is running on outside of the university main network, so I couldn't access to this one. But in your university website, you should be able to get this one straight on without any issue. And then once you get this one, you click on this software, you can start to run the program. So for me, I got different versions of the Autodesk robot in here from Autodesk, and then to allow me to prepare the materials, and then use a slightly different version is a 2024. They are very similar to the 2020 and 2022. It doesn't matter which version you have, and then they should be work exactly the same. So because I got this version from the Autodesk already, then I will use this that version to do the demonstration, but you can use the university version that will give you the exactly the same result. So I now start this Autodesk robot structure analysis software. So give it a minute. So once done, then you need to make sure you select a new project. Just select a new project in here. So in the type of the project, and then the screen pop up to show you what type of the project the project you're going to handle, and then there was several different type of the structures you can do, and then the one we are doing is actually the 2D structures. So you might need to make sure you use this one. You need to click on this one, a 2D, not 3D. Okay, so it has to be 2D, and also not the frame structure, because this member, this will our structures only have tension and compression. It's a truss structures. We have to use these truss structures proper models to do this one. So once you click on this one, will bring you to this user interface, allow you to draw the structure properly, and allow you to apply the bonding condition, loading, so on and so forth for this one. So the first thing we need to make sure is that the dimensions you're going to use. So in the dimension in here, so we going to use even for the for the size, for the length of the structures, we're going to use the millimeter. So we're going to change this one a little bit, and to make sure that all the details you got in here match the details you're going to input from the problem statement. So what you need to do is you move your cursor here, and then double click on this one. So it will bring you this job reference menu. You can use this, you can change it in here, or if you want to change this one in the future, you can also go into the tools, and then also click on the job reference, job preference, and then that will bring back the same screen for you. So what you need to do is that you need to click on the unit in here. So make sure that the unit you're using in here, so the dimensions, the dimensions here. So the dimension here, you need to use these millimeters, change to millimeters in here. Okay, so that's what you need to do only. So this one is a kilonewton, so we keep them there. So that's all the two things we need to do for this case. And also for the material, what we using in here is a very special one, because the normal steel is a 210 or 205 from British Standard, but in our problem statement, if you still remember correctly, so that's 200. So we need to create these special materials for our analysis. So what I'm going to do is that in here, the material, I'm going to click on modify, and then we can then go to the others, and then I can then define a new one. So if already have something there, you can also delete that one. Say if you already have a truss mat or somehow during the practice, and then you already create one there, you can click on select that one and click on delete. They will delete that type of material as well. So for us, what we need to do is that we need to change this one, and then the name, I give a new name to it, is truss material, so truss mat. And then the only thing we need to do in here is only the Young's modulus. We just change this this 205 to 2000, because remember in here is a megapascal, and then convert to the problem statement is kilonewton that per millimeter. So we just need to make sure this is 205, and then the 5 here change to 0. So that's give you the same Young's modulus in there. You can do the unit conversion yourself after class. So after we change this one, make sure you click on add. Okay, click on add. so you can add that one on. Then you can have this new material down. So if you say, for example, if you click back, click here and then click back again, you can see the truss mat is still there. That's correct. And then if you click down the user, then the other one, predefined one, is still there as well. So this will be correct. So after that, we don't need this screen. Then we can click on OK and then close the screen, and then also click on OK, close the second one as well. So after that, what we need to do, we need to create the grid. So create the grid. So what we need to do is that we have a grid line here and another grid line here. So in Y direction, we only have one repeat. And then for X direction, we have one here, just first repeat and second repeat. And between the repeat is 3 meters among the distance. So what we're going to do in here, oh, by the way, once you click on OK, you can already see this one is changed to millimeter. So make sure you know that it's changed to millimeter already. So to set up the grid, so we use these axis definitions in here. So we click on this button, bring back this information. So we only have, make sure you see this X and Z in here. Okay, so if X and Z, then what we can do is that we can set this one to X direction is 2 repeat, and then the distance between each repeat is 3000 millimeters. So after that, we click on Add, so we get you get 3 lines in there. So Z direction, we only have 1 repeat, and then but leave this position starting from 0, so it's all from the original point 0 and 0. Start on this grid. So this will be 3000 as well, and then only 1 repeat you add on, so you get a 2 axis line in this case. So once done, then you can click on Apply. You can see the grid is generated in there already, right? So after that, we just need to draw them one by one, and then line by line we can create these truss structures. So before we do that, we need to also set the cross-section properties for this case. So we need to make sure we create a new cross-section, member sections. So we click on this one. And then you can see this is all the existing one. We are not going to use either one of them. So we just need to click on a new section definition. And then we create maybe a section that members using this detail in here. So we can click on the parametric one, and then we can use this one rectangular one, but we click on solid, and then as you can see the material here, if you want to drop down, there's nothing truss mat we can use. There's no truss mat, the one predefined can be used in here, doesn't matter. We're going to change this one later on. So what we need to do is make sure it's solid, and then that's the one we allow us to recognize this one better. We change this one to truss that sections for here, and then the B here, let's say put the 10, and then because it's 1000, so that's the other side has to be 100 to give you altogether the area times together give 1000 millimeter square in there. Okay, so once we done this bit, and then we just need to click on Add. So you can see this structure, this cross section. We close this one in there. Then we come back to this one. So this truss add has been added to this place here already. Then after that, what we need to do, so we need to maybe set this material. So we leave it that one there. We come back to here, just click on material. So let's bring back this material table, but you can see now this time we have a truss that section in here. But in checks, but the material is S275, the steel material is not correct. So what we need to do is that we just need to click on this one in here, all, and then we need to select down here this material here, and click on all, and click and then select from this drop down menu. So you can see the last one is the truss mat. So we click on truss mat in here. So once we click on truss mat, then we come back to this cross section, highlight this cross section, and then I click on apply. Then you can see the material now change from the steel S275 to the truss mat. That's our predefined structures in there. So once done, then we can close both sections, both windows, and then that's set up ready. So we are about to draw these structures, and then I will stop my video in here and then continue in the next slides. Now we have done this material and cross section and grid definition. So we have got all the axis set up already as well. So the next one is ready to build our structure virtually in this graphic user interface in Autodesk Robot. So to do that, what we need to use is use this button in here. So the member button in here. So we click on the members, and then using the simple bar. So make sure that you use a simple member, and then the materials is the cylindrical section is set to the truss sections for this one as well. And then make sure you move this window to somewhere that's not blocking your view. Then you can draw these structures. So when you move your cursors to this one, you can see this cursor is switching to the drawing mode. So for the drawing mode in here, then what you need to do is that you need to draw these members one by one. So first one is that starting from this point. So when you draw this line, it has to be very precise. You need to start in for these 0, 0 coordinates in here. So what you can do is that you can move your cursor close to this intersection, and then this cursor will also snap onto that intersection. So after that, you can click on this one and then drag this line onto the next one. So this is where the next end node is located. So you can also see that the cursor is also snap onto this intersection in here. So once you click on this one, then the first members has been confirmed. And then you can continue to draw the next line by move your cursor close to this node again, and then click on this node, and then draw to the next one. So make sure you draw this one, you move your cursor very close to the intersection, so they snap to that intersection, and then you can precisely draw the members in there. And sometimes you do make a mistake. For example, if I draw this line, I draw this one, I need to snap to this one, but I make a mistake, I click in here already. So that will be additional members in there you don't want. So if that happens, what you need to do is that you need to come back to this window, but make sure you close this window first. So after that, you can select this bar and then press on the delete key. So this member is deleted. But however, remember, you can see there's still a note in here. There was a red small dot in here. So there was a note in there. You also need to delete this one. So you need to click on here and select this one, and then delete this one. Press the delete key. And then also you can draw a box, select this area, and then you can see this one is selected and then turn green. Then you click on delete as well. So that has been deleted completely. Then after that, you can continue the drawing. So I can then come back to this member, click on this one, and then continue to draw all the rest of the members. So we click in here, and then also we snap onto this point and click on here, and you got this members set up. So the last beam, last bar is from this one to here, and then that's it. So structure has been built. So if you want to have a look at the node you assign, you can click on the node number. That's give you the number in here, 1, 2, 3, 4. Okay, and then also you can click on the member that mark on all the members numbers for you as well. So using this one, so using these two in here. Okay. Then after that, you can also use this triangular, which is section shape, and then that will allow you to see the shape of the structures in here. So these structures, if you really want to see the 3D, you can also do that one. But before you do that one, be safe. We close this window because otherwise you maybe accidentally draw an additional member somewhere. Okay, once you're done, if you want to really show the screen, you can hold on the shift key and hold on the middle button, the wheel of your mouse, and then hold on that one. Then you can turn the structure, and then you can see the structure in there. Okay, so this is show you the 3D structures you get in there. And but if that's the case, after that one, you will see that the structure here will change completely, and then sometimes you may not see the grid line clearly in this one. Then you maybe need to switch back to proper one. So before we switch back to proper view on top, and then I show you how can we rotate these structures. So basically, you hold on the shift key, and then press on the wheel in the middle of the mouse, and then hold on to both things, and then you can turn your mouse, then you can rotate this structure to different location you want, and then release that stop. Okay, so once done, then what you can do is that you can switch back to the coordinates. The coordinates we have is xz 2D coordinates in here. So we click on this one, so they come back to the original direction. And then because this may be actually the real size, the shaded that shape of the truss member, we don't need that one. Really don't need that one at this stage. So we can click on the section shape and return it back to the normal. So after that, what we need to do is that we need to apply the support to these structures. So I'm going to apply the fixed support. So we then select this fix in here. So make sure you select the fix in here. Okay, this is a highlight. And then you move the cursor, you can see this cursor is changed to a fixed that symbols in there. So you click on number 1 in there, so you can see this fixed point has been allocated, and the second point in here, this will be supported already. So for the the support is done, then we need to apply the loading. So to apply the loading, we need to create a 2 case. So case number 1 is here. So case number 1 is here, and case number 2 is here. Because we can then to analysis, if I only have this loading, what impact to the building, and then if I only have this loading, what impact to the building. Then we can also combine them to have a combined loading as well. So this function will be very convenient if you analysis in the structure, if you have a live load, dead load, wind load, and then maybe the other snow loading. They have different type of combination, then you can still do that one that properly. So now we need to apply the loading. So before that one, as we said, we need to create the 2 load case, one for this one, one for this one. So we just need to use the button after. So using this one, and then simply to add 2 load case is very simple. You can add, you can just click add 1 case in there, and then the case is generated. Once you generate this one, you can notice that one also create additional case in there. If you drop down here, now that there is no loading in here at this moment. Okay, so there's no loading at this moment. So sorry, not the loading, there was no second loading at this moment. So what you need to do is that you need to click on another one. So this one will now add another case 2 in here. So once we're done, then we can then apply the loading to the actual structures. So to apply the loading, we don't need this window anymore. So we just simply just close this window, and then we switch this back to the proper case. So let's choose the low case 1 only. And then to choose the load one, then we need to apply the loading. So what you can do is by click on this button in here. So click this button. Then we only have make sure this is that load one, and then this is also set in the current case is that load one, and then we can select this node forces in here. So this one is the 10 kilonewton along the x direction applied to the number 4. So we can add this one in here. So once you come back, then you can see you move your cursor away from the window. You can see this is a applying mode of this structure. So you can apply the forces to here. So you can see this force now has been added. So if you want to see how much this loading has been added, you can maybe come to this point and then click on this small dot. Then you can see that's x equal to 10. Then the next one is it will belongs to the next load case. So what we need to do is that we need to click on that load case in here. So which is second case, and then second load case, and then make sure this also switch to the second load case as well. Then we can apply the loading. But remember this time, make sure this change to 0. And then the z direction will be minus 10 as well at this location. So if you click on add and then move your cursor away from the window, you can see that's changed to applying mode. Then you click on the number 3. That's loading also applied in there. And then that's to loading separately. So let's close. We don't need the load definition window anymore. So we close this window. So you can see this is a case 1. Oh, case 1 and case 2. Those are not showing in there. So let me see the load symbol in here. So yeah, I need to press the load symbol in here. So let's click on that load 1. So make sure that this one switch on. So this one load symbol switch on, switch off, switch on, switch off. Oh, sorry, switch off, switch on. Okay, and then so we can change to the that load case 2. Then you can see this loading has been applied properly to these structures. And then what we need to do is that the second one, we need to go to the combination, because we want this loading. I want to see the third case is combined of these two loading, so we cannot use this separate load case function anymore. We need to go to here, go to the loads, and then we need to manually create that combination by click on this one. And then so that will be the load case combination 3. So this but it's a combination 1, but it's a load case 3 case 3. So we can then set the parameters. So set the OK, click on OK. So this is a name, so we want to add, and then we can leave it up. If you're not happy, you can change the name, the combination to different names as well. So we click on OK. So they bring up this window, allow you to combine then. So make sure that you select the first one. Click on number 1 in here. So you see arrows pointing to the number 1. And then the factor is really number 1 in there. And then you click on this single chevron. So they bring this case 1 to the right hand side. So that's 1 times the case number 1. And then also the second case is also the factor going to be 1 as well. So then you can add this on. So you got the both cases that apply to these structures. So after that, if you click on apply, and then this structure has added onto the structure, but looks like nothing happened. But if you close the window, and you can come back here to switch to the third case combination, you can see all these two loading is showing up in there. So before we that run the analysis, we also have one more things to do, because in our analysis we didn't consider the member force inside the structures. Of course, you have material. If it's steel or concrete, they have self-weight. Self-weight will also contribute to the loading, but in our theoretical study, we didn't consider the self-weight as well. So we need to get rid of the self-weight. So to get rid of the self-weight, what we need to do is that we need to go to this button to use the tables. By click on the tables in there, and then you drop down and select the loads in here. Okay, so click on loads and then click on OK, and then you can see this self-weight in here that is already on top of the dead load case 1 and 2 is already add that self-weight onto this structure already. So what you need to do is really click on here and right click and then delete this one, or maybe no, may not have this one in here. So basically you need to do is highlight this one, and press the delete key. So this one will be deleted already. So once done, then we can close this window by click on this one, close this window, and bring back these structures in here. So after that, what we can do is that we can have a look at the support. So press this one, support is coming back, and then load symbol is already on, and then lowercase 1, lowercase 2, and lowercase 3. So that's the final one we're interested in. So for this bit, right? So now if everything's set, then you should be ready to run the analysis. So if you click on run the analysis in here, just do the calculation. So this will bring up the finite element window and then finish analysis in seconds. That's already done. Then once we got this one, then you can have a look at the deflection by click on this one in here, right? So you got the default deflection for the structures, and then if I really want to find out that what is the deflection for the node 3 and node 4, so you can click on this table in here and then just select this to the node displacement in here. So click on here and then click on OK and bring back these windows in here. So the displacements here is really small at the moment, so we couldn't see that the details in here. So that what we need to do is that we also need to come back to this tool and then drop reference in here, and then we need to click on the units in here, and then so we're going to use the dimension for this one, section dimension. Let me check where it is the others. I think a displacement here. So displacement here is using a millimeter, but only the 1 decimal. So we need to maybe use 2, 3, maybe 3, 4, 5 decimal. Let's say, if you not necessary to be that accurate. So 2, 3 should be good enough already. So let's see, we use 5 to compare with our Excel calculation. Then you can click on OK, and then after that you can see all the deflections is showing in there. But the really important one is actually the number 4, the case number note number 4, case number 3, and that number 3 is and then case number 3 as well, right? So let's compare the results we got using the Excel, and then we bring back these displacements in here, so we can move this one to the displacement in here. So that's give us the displacements in here. So number 4, X direction is this one. You can see this one and compare to this one, and this one compared to this one, they are exactly the same. So number 3 with these 2 loading on, so it's actually number 3, case number 3 is this 129 A53, and then the other one is this one, and they are exactly the same. They're exactly the same, right? So this is a very accurate results. And then we can also, if the displacement you satisfied, we can have a look at the member force as well. So if you want to have a look at the member force, you click on this one in here, and then just select the member force, which is in here, and then click on OK. So that bring back all these forces in here. So if we want to find out the member force, we can have a look at the member force we got in here. So this is the member force. So member force, what we need to do is 5 of them, but we really look at the only one is the this what do you call the case number combination 3, case 3, right? So number 1, number 2 is number 1 is 0, so member number 2, member number 2. So but we need to make sure that number 2 is mapped onto, because the member 2 could be different to the number 2 we define, depends on how you draw it. So now our number 2 is defined like this one, but look at the our oh sorry, I just click on this one, so I bring this table that a little bit away from this one, so I can see both together in one screen in here. Okay, then you can see actually our number 2. Have a look at this photo in here. So our number 2 is actually the number 4 in here, right? So because of this, so we need to compare our number 2 in here, so to number 4. So let's go into the member force in here. So the member force, that's number 2 is this one, 28, and then compared to 28 force compared to the number 4, so number 4 is 28 in here, right? So it's very accurate. And number 2 in here, so our number 2 in here, so in our Excel in our problem statement is actually number 3. Okay, number 3. So number 2 is number 2 here should be this one, is member number 2, and in case number 3, so that's 14 somehow, right, for this one. So that's negative 1. Yeah, number, so the no, sorry, I maybe make a mistake. So this this number 3 map onto this number 2. Okay, so basically we need to find out number 3 here. Number 3 is a negative 14 by 14 map onto number 2. So number 2 is actually this one. Oh, it's positive. Number 2, case number 3. Oh, 28. Oh, okay. I think what we need to do is this is what we have defined. So this is note number 1, this member number 1, note number 1, and the case number 1. So we get 1 force. So here is a case number 2, and then so case member number 2, and the note number case number 2, that note number 2, and member number 2, and number 2, case number 2. So this means we are talking about the force in here, the force in here. Okay, so this force in here. So for the member number 2, and then note number 2 is talking about this one. In case number 1 is this force in here. So this when you have this force in here, then this member force, at this case, for this case, there was no force in here. there's 0 force in here. Okay, then for only this force. Okay, so the case number 2 at this node, and case number 2 and the joint number 2, and then the low case 2 which has this force only, that's equal to the 14 15. So 14 15, but it's acting on this one. So whether this one is a positive, this is a finite element positive, but doesn't mean it's actually the tension and compression. So you need to identify whether the force in here at this location along this direction is positive, whether they're going to be a compression or tension, is what we discussed in previously in the slides before. So let me bring up these slides for you. Just give me 1 minute. Okay, so now we got this one in here, right? So we got this one. So this is the positive, and then so this, if this one is positive, and then this one is positive, then this and the tension in this one, they will be opposite. So this all the same force, but they have a difference in between. So that's why you can see that you get a one side is positive, one side is negative. You need to identify which part is the positive, which part is negative, based on this one. So the finite element in the in this Autodesk robot, he only give you this number, but they didn't give you this number. So you need to translate this force yourself in here. But when you translate this one, you can see that what we join is 2 to 3. So if this force in here, for this case, if you put a loading in here, surely this will be under compression, right? So the node force for node number 2 at 2 is the positive. So which means this one pushing this one in to the node 2. So this element will under compression. So this for sure will be negative forces. So that's match onto our calculation in here. Okay, so match onto our calculation in here is a negative force. So in our program, we automatically do this kind of identification already. But in finite element, when you got this result, you still need to translate this information into the table. Is it a member force in compression or tension? This one in there, right? So this is a member force, and then if I really want to have a look at the reaction force, so what I can do is that I close this window and then use this table again, and then we go to the reaction force. So reaction force in here, and then you can click on OK. So then they bring up all this reaction force for you in here. So the key one is the one that we want to compare, right? These two forces. So let's bring back the reaction force in here. So this is a reaction force for our case. And we are talking about the node number 2 is a 10 and 30. So case number 3, case number 2 is this one, 10 and 30 in here, right? So they match onto these two forces perfectly. So 10, 30. And then node number 1, case 3 is a minus 20 and minus 20, minus 20, minus 20. That's perfect results in here. Okay, so that's conclude our first demonstration for Autodesk robot to analyze these 5 bar elements in here. I hope you enjoyed.